Question 35. A random variable is normally distributed with mean 0 and standard deviation 1. The table gives the probability that this random variable is less than z. The probability values given in the table for different values of z are represented by the shaded area in the following diagram. The scores in a university examination with a large number of candidates are normally distributed with mean 58 and standard deviation 15. Part A. By calculating a z-score, find the percentage of scores that are between 58 and 70. The raw score of 58 corresponds to the mean, hence its z-score is 0. Now the z-score for the raw score of 70 is given by the z-score formula, which is raw score minus mean in brackets divided by the standard deviation. So 70 minus 58 in brackets divided by 15 is equal to 0.8. Now we want the percentage of scores that lie between a z-score of 0 and a z-score of 0.8. Now from the table, the percentage of scores below z equals 0.8 is 0.7881. So I'll just show the table there on the screen. So we have a z-score here of 0.8, and from the table, z equals 0.8 corresponds to 0.7881. That means 78.81% of scores lie below or to the left of z. But we want the percentage of scores that lie between z equals 0 and z equals 0.8. Just put the diagram back up on the screen. So we want the percentage of scores that lie between 0 and 0.8. Now we know from the characteristics of the standard normal distribution, half the scores lie to the left of 0, or a z-score of 0. So 0.7881, so that's this whole shaded area, if we take away 0.5, we get the percentage of scores that we want. So the percentage of scores between z equals 0 and z equals 0.8 is given by 0.7881 minus 0.5, and that equals 0.2881 or 28.81%. Part B. Explain why the percentage of scores between 46 and 70 is twice your answer to Part A. The z-score for the raw score of 46 is given by 46 minus 58 in brackets divided by 15, which equals negative 0.8. So we're just using the z-score formula that we used in Part A. Since the normal distribution or the normal curve is symmetrical about z equals 0, then the percentage of scores from z equals negative 0.8 to z equals 0.8 is twice the percentage of scores from z equals 0 to z equals 0.8. If we have a look at the normal curve, if that was z equals 0.8, then z equals negative 0.8 would be roughly here. And this area here from z equals negative 0.8 to z equals 0.8 would be twice the area from z equals 0 to z equals 0.8. Therefore, the percentage of scores between 46 and 70 is twice the percentage of scores between 58 and 70, which means it's twice the answer that we obtained in Part A. Part C. By using the values in the table above, find an approximate minimum score that a candidate would need to be placed in the top 10% of candidates. Being in the top 10% of candidates implies being above the bottom 90% of candidates. If we just go back to our normal distribution, we want the bottom 90% to be in this shaded region here. Now looking at the table, the bottom 90% corresponds to a z-score of 1.3. In other words, candidates in the bottom 90% will score less than a z-score of 1.3. So being in the top 10%, a candidate will need to score above a z-score of 1.3. later on we'll need to convert that Z-score into an actual or a raw score. So from the table, the bottom 90% of candidates will be below a Z-score of 1.3. Now we need to find the raw score or the actual score that corresponds to a Z-score of 1.3. So we need to reverse the Z-score formula that we used in Part A. So a Z-score of 1.3 is equal to x minus 58 in brackets, where x is our raw score, divided by the standard deviation of 15. We're going to move this divided by 15 over to the other side, and it becomes a multiplication. So 1.3 times 15 is equal to x minus 58. Now 1.3 times 15 is 19.5. So the equation simplifies to 19.5 is equal to raw score minus 58. So isolating x, which is our raw score, we get x is equal to 19.5 plus 58, which equals 77.5. If we round that up, we get 78. Therefore, a candidate will need to score at least 78 to be placed in the top 10% of candidates.